Hi there, this is Simple Harmonic Motion Lesson 4, Spring Mass System. We're going to do some recap questions first of all. So if you want to pause and have a go at this one. Then I'll take you through the answer. Which one of the following graphs shows how the acceleration, A, of a body moving with simple harmonic motion varies with its displacement, x? So if we remember, the quick way of doing this one is because I have shown you this graph before. Acceleration is equal to minus omega squared x, and that's the equation. It's already in the form of a straight line because acceleration is on the y-axis, displacement is on the x-axis, and this would be the gradient, and there's no plus c intercept, so straight in the form of a straight line, negative gradient. So the answer is D. Let's look at the next one. So you want to pause and have a go at this one. A body moves with simple harmonic motion of amplitude A and frequency B over 2 pi. What is the magnitude of the acceleration when the body is at maximum displacement? So the thing that we need to take into consideration here is maximum displacement and acceleration. Acceleration at maximum displacement occurs, the maximum displacement is where the maximum acceleration occurs. So acceleration is equal to minus omega squared. And instead of x, we're going to put A for amplitude. That's the maximum displacement. Then we just need to do some substitutions. So frequency is B over 2 pi. So we need to substitute in acceleration is equal to, and omega is 2 pi f. We should know that one now. So that would be minus 4 pi squared f squared a. So that's just the equation omega is 2 pi f squared to give 4 pi squared f squared. Then we just need to substitute in for the frequency b over 2 pi. So acceleration is equal to minus 4 pi squared b squared divided by 2 pi is squared would be 4 pi squared times a. So the 4 pi squareds cancel out, and we're left with acceleration is ab squared. There is a negative, but it's just the magnitude, so it doesn't matter. So acceleration is ab squared, which is answer C. One more to look at. If you want to pause and have a go at this one. A ball of mass m, which is fixed to the end of a light string of length L, is released from rest at x. It swings in a circular path, passing through the lowest point y at speed v. So we've got speed v. Write an expression for the tension T for the string in the string at its lowest point. So there. So we need to identify what's happening. So the tension in the string would be going up. The weight would act down, mg, and the centripetal force, mv squared over r. The reason I've used mv squared over r is because it says speed v rather than using mr omega squared. Now we could use this, but in this instance, no, because it gives v in the question. So then we need an expression for the tension. So we need to apply the sum of the forces is equal to mv squared over r. So the sum of the forces will be, we're going to take up as positive because the mv squared over r is going upwards. So the sum of the forces is T minus mg because that's acting down equals mv squared over r. Then we just need to rearrange to find T. So we need to add mg on the right hand side. So I'm going to do that, but then I'm going to factorize and just tidy up a little. So that will be plus mg. So we can pull the m out, factorize, and then have v squared over r plus g. And that's the expression for tension. Some new information next. So what I'm going to do is to show you where an equation comes from for a mass that's oscillating on a spring. So we have if this is moved down from if this is on a spring and it's moved downwards and then it's allowed to oscillate, it's going to have a restoring force that acts upwards. And that restoring force on a spring is equal to Ke, or minus Kx, x being the displacement of the mass. Then the force is equal to, we can substitute in Ma, Newton's second law, so mass times acceleration is equal to minus Kx. And then because this oscillating mass will exhibit simple harmonic motion, we can substitute in, you'll see now, so m, put a minus, and acceleration is minus omega squared x equals minus Kx. The x's will cancel, the negatives will cancel, and omega squared is equal to K over m. Then we can use omega as 2 pi over t. So if 2 pi over t squared would be 4 pi squared over t squared equals K over m. Then if we rearrange to find t, we get the time period. So that'd be t. Take that up, take the m up, bring the k down, square root everything. So the time period will be equal to, you can attempt this yourself, 2 pi square root m over k. I suppose you could flip both sides, flip both of these. Bring the 4 pi squared down and then square root. And this is what you end up with, this expression at the bottom. So that's where it comes from. So you can take some more notes now. Mass spring system. So if a mass m is hung from a spring of spring constant k and set into oscillation, the time period t of the oscillations is given by t equals 2 pi root m over k. That's the equation that I just shown the derivation for, if you're interested. Reminder from AS physics that k is the spring constant and it's the force in newtons required to cause a change of length of 1 meter. So k is equal to F over delta L, change in length, and it's measured in newtons per meter. So let's pause and have a go at this question, and then I'll take you through it. A spring extends by 6 centimeters when a mass of 4 kilograms is hung from it near the Earth's surface. If the mass is set into vertical oscillation, state or calculate the period A near the Earth's surface and B on the surface of the Moon, where G is equal to 1.7 meters per second squared. So what we need to do, we're going to use the time period is equal to 2 pi square root m over k. And we've got the mass, 2 pi is obviously a number, we just need k. So k is equal to force over extension. And you can use x or delta L or E, it's completely up to you. So the force will be the weight, and the weight we will get from the mass. So that would be mg divided by the extension. So let's put some numbers in. So we've got 4 times 9.81 divided by the extension, 6 centimeters, so that's 0.06 meters. And that gives a k value of 654 newtons per meter. Then we just need to put our numbers into the equation. So t is equal to 2 pi square root, the mass is 4, divided by k, which is 654. So that gives a time period of 0.49 seconds. B. So if this happened, so we took it to the Moon where G is 1.7 meters per second squared. So the time period on the Moon is also 0.49 seconds. This equation, so let me just clear this now that we know. The equation t equals 2 pi m over k. Does not have g in it. And the spring constant is the spring constant. The spring constant is force over extension. So you might be thinking, well, if we take that to the moon, we're going to have a different force. You would have a different force. If you applied a mass of 4 kilograms on the moon, you would have a different force. But you would also have a different extension. And you would still get the same answer as what you got last time. You would still get the 654 newtons per meter. And thus get the same time period of 0.49 seconds. It's an important one to remember. Exam boards love to examine this to see if you know. And you'll see that in next lesson. So one more question. Tricky one. Let's have a go at it. So let's pause. The period of vertical oscillation of a mass spring system is T when the spring carries a mass of 1 kilogram. What mass should be added to the 1 kilogram if the period is to be increased to 1.5 T? So the equation, T equals 2 pi root m over k. So what I need is a relationship between T and m. And so what I'm going to do is square everything first of all. So T squared is equal to 4 pi squared m over k. Now for both these situations, the spring is physically the same. It's the same spring. So what we can do is write T squared over m, which is what the relationship which we're looking for, is equal to 4 pi squared over k. And the 4 pi squared over k is just a number. It's a constant. So what we can say is that for time period 1 and mass 1 is equal to 4 pi squared over k, we can also say that the second scenario, so the second time period squared divided by the second mass, whatever the mass is also equal to the same constant. So what we can do is say T1 squared over M1 is equal to T2 squared over M2 because they're both equal to the same constant, the 4 pi squared over k. So I'm going to do that now. So we've got time period 1 squared over mass 1, whatever that may be. We'll worry about that in a second, equals the second time period squared divided by whatever the second mass is. Then in the question, so time period 1, we're just going to call T1 squared over mass 1, which is 1 kilogram, equals time period 2. So what we've done is multiply the original time period by a factor of 1.5. And we need to square that 1.5 to give 2.25. So this one will be 2.25 lots of T1 squared divided by, now it was the original mass, which is 1 kilogram, plus some unknown mass. So we've got 1 kilogram plus the unknown mass. So what you'll see is that the T1 squareds cancel. And I can bring the 1 plus m up from the bottom right up to the left hand side. So therefore, we get 1 plus m equals 2.25. So you can see from that, it's 2.25 minus 1 to give m. So 2.25 minus 1 is 1.25 kilograms. Tricky question, hopefully that went okay. You might have done it in a different manner. As long as you got that answer, that's all that matters, the 1.25 kilograms. So thanks for watching, and I'll speak to you soon.